So where is all of this circle and square business leading us to? It's leading us to a conversation on binary numbers. So when we were using two symbols, circles and squares, you created your own number system. What else can we communicate using only two symbols? And is there a limit? Well, what you should be thinking about is if we have one place value and we have only circles and squares, we can create two different patterns, right? I can create a square or I can have a circle. So just two different patterns. But if I increment the number of place values to 2 positions, I can have a square and a square. I can have a square and a circle. I can have a square and a circle like that. Or I can have a circle and a circle. Okay, so I can represent 4 different things using only 2 different symbols, right? With 2 place values. And when you did the activity, you discovered that with 3 place values, you can come up with 8 different patterns. And since we're starting to see a pattern with this, we can actually map a meaning to each of those patterns. So we can map 0 to the pattern circle, circle, circle. So whenever we see a circle, 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 we know we're talking about the quantity 0. We can map circle, circle, square to the quantity of 1. And we can map circle, square, circle to a quantity of 2. So using 3 different place values, we can map the numbers 0 through 7 to each of those 8 different patterns. And why are we starting at 0? Well, it turns out computer scientists start counting at 0. And this will be important later on when we start programming. Let's map this to the number system we're most familiar with, decimal numbers. So number systems help us express and reason about quantities, right? I have 2 oranges. I have 3 children. Early number systems were merely a system of tallies that allowed humans to record and perform simple arithmetic with values. Then the number system was invented, and the number system we use today uses the concept of place value to allow us to express any value we wish by just combining only 10 symbols. And these are just shapes. Instead of circles and squares, we're just going to use 10 different shapes, right? 0 through 9. Someone just arbitrarily decided that this shape would represent a 0, and this shape down here would represent 9. And because there are 10 different symbols, we call this a base 10 number system or decimal. And so if I look at this number, 099, what comes next? What was one of the rules that you came up with when going to the next number with circles and squares? Well, if my rule is when I get to the last symbol in my number system, I need to start over. And so I'm going to start over with a 0, but that means I need to put a 1 in the next place value. And so if I were to put a 1 in the next place value, that would give me a 1 and a 9, which would be 10. And so I can't represent the number 10 using only 1 digit, so I have to assign that place a 0 and then carry the 1. So I'm going to go to the next number after 0, which is 1. And so that's the same thing that you should have come up with the circles and squares. And so where is this going? It's going to binary. So binary is a number system with only 2 shapes, but instead of using circles and squares, we're just going to be using zeros and ones, because it turns out a computer is an electronic device. And if there's electricity on, then a computer can represent that as a 1, and then if it's off, it can represent that as a 0. And so we can have all of these different combinations of zeros and ones to represent an infinite amount of numbers. So let's count in binary. So instead of our circles and squares, I'm going to convert those to zeros and ones. Wherever I see a circle, I'll put a 0, and wherever I see a square, I'll put a 1. So when I'm counting in binary, I'm going to start out with 0, and then I'll go to the next symbol, which is a 1, and then I need to go to the next symbol, which is a 0, but I'm going to have to add 1 in the next place value. And so then I'll add 1 to my first digit, and then when I add 1 again, it's going to cause, I have to go to the beginning of my symbols, which is 0, and then a 1 carried over would also cause me to go to a 0 starting over, and then I would go back to 1. So it's just replacing the rules that you came up with zeros and ones instead of circles and squares. So in binary, if I want to write the number 4, or if I want to store the number 4 in a computer, I would have to say 1, 0, 0. So binary is the language of a computer, and binary means 2 states. The 2 states are sometimes called ones and zeros, or true or false, or on or off. The essential characteristic is that a single binary device can be in just one of 2 possible states, right? It can either be on or it can be off. And a good example is a toggle switch, such as a light switch. You can turn it on and off, but not in normal operation. We're not talking about dimmer switches, anything else. So a light switch holds just 1 bit of information. So computers can hold the state of electricity as a bit, either a 1 or an off, as a toggle switch. The computer is made up of these tiny on and off switches that are easy, cheap, and reliable to make, and millions of them make up the circuits that fit into the small area of a silicone chip in a computer. It may be hard to imagine, but we can represent numbers, text, sounds, and images just with these on and off switches. So when the switch is on, it's a 1, and when it's off, it's a 0. But we saw with the circles and squares, if we increment the number of places, we can hold more information. You just have to add another place to hold more information and increase the number of patterns. Take a look at this video. Go ahead and pause the lecture video and watch this video. And before we look at how information is stored as binary signals, on or offs, let's see in detail how a circuit works.